This is a report on the experimental work that has been carried out in the School of Engineering Information Technology at Sheffield Hallam University between the 5th of October 1992 and the 23rd of April 1993. The work has been on an edge damage detection system for steel strip. The original project draft was given to me by my supervisor, Dr. Bruce Morrison of BHP Australia Limited. BHP Steel in Australia is where I did my industrial placement. BHP was not able to fund the project directly, but they did give me permission to seek help of British Steel. Dr. Graham Jones of British Steel has provided me with a frame store for use on the project. Without his help, this project would not have been possible. The aim of this project was to detect damaged edges in steel strip prior to coating so as to prevent damage to the rollers, which would then print a pattern on the strip edge, downgrading the quality. Due to the way the strip is coated, any edge damage can damage the soft rubber rollers that are used to apply the paint. If the rollers are damaged, then a pattern will be created on the strip. The system will detect damage as it appeared, then send a signal to the coater head controller for it to remove the coater head for the duration of the damage. This system would have a dual benefit. 1. The amount of damage would be reduced, and 2. The amount and position of the damaged steel could be logged and used later for costing. This shows how the paint line of BSC is laid out, with the entry and exit gates right opposite each other. Directly following the entry gate is the entry accumulator, followed closely by a tension leveler. Then there are some pre-treatment bars. After the pre-treatment, an undercoat is applied, followed by the top coat. The point just after the pre-treatment and just before the initial undercoat is where this system would be installed. Pre-painted strip has many uses, from white goods such as fridges and washing machines to fencing and roofing materials. British Steel is the world's largest single producer of pre-painted strip and is the UK's largest single consumer of paint because of this. Here are some of the white goods: fridge doors. Two methods have been tried for the initial edge position location: filtering, which is a more commonly used method, and edge tracking, which is a method partly developed by the author. Filtering was tried because there are many tested algorithms available that can be used to detect and enhance edges. The filtering algorithm that was used was based on Laplacian methods. The function works well, but it is slow and is susceptible to noise. When the filtering has been carried out, the image then has to be smoothed to get rid of spurious noise spikes. Any image processing can be very slow due to the amount of data to process. In this case, each screen is 512 columns by 256 rows, which gives 132 kilobytes of memory per image. The window function reduces the amount of processing to be carried out by windowing a smaller section of screen. With a small window around one edge of the strip, reducing the image size, this makes the filtering function work faster. The window has to be wide enough to allow the strip to wander and long enough to view as much of the strip as possible. This is as far as the filtering function was taken due to speed and problems with noise. The second method that was tried and adopted was edge tracking. The edge of the sheet is tracked as it passes through the field of view. Edge damage is detected when the intensity profile across the strip edge changes more than an allowable amount. If there is no damage, then the intensity profile will look like B. If the damaged area is to the left or to the right of the edge, then the profile will change and look like A or C, respectively. The high values are the white background and the low values are the dark strip. For both windows, all the pixels in a row are added up and then divided by the row length. This is so that all the values are relative. There is then a table of data values with as many elements as there are rows in the window. The table is then stepped through until the mean level is crossed. This is then taken as the strip edge. When both edge locations are known, A function then sums the 10 pixels in 10 rows parallel to the strip edge across the screen from one window to the other. The 10 sums are then divided by the distance in pixels between the two windows and the intensity profile is checked. The 10 rows are plus or minus 5 pixels off the edge. This shows the two windows placed over the two ends of the strip. The windows have to be high enough to allow for strip wander and wide enough to allow an accurate initial edge position to be calculated. The thick line that can be seen flashing is a tracking function following the strip edge. In practice, none of the rows would be visible as they would slow the system down. All the rows that are summed are shown here. The function has been slowed down to reduce video distortion. Though the strip may move up and down, the edge tracking function will not fail. It will only fail if the lighting conditions change abruptly, i.e. if one of the background lights fails. This shows better how well the tracking function works. The single flashing line sits on the edge of the strip. The flashing is caused by the frame store grabbing a new frame. Two methods have been used to determine whether damage has occurred. The first shown here is by calculating the Euclidean distance. The Euclidean distance is the difference squared between the template profile and the current profile. A threshold is used to differentiate between a good and bad edge. The lines at the top of the screen show the Euclidean distance threshold. If the edge profile changes too much, then at the point a peak will appear. In this case it looks like a valley. The lines on the bottom of the screen show the profile of the strip edge. The difference between a good edge and a bad edge can clearly be seen. The first couple of seconds of this scene showed a good edge. The plots can be seen now are a sum of sort of damage. The change in color of the lines is not important. They change color so that I can see which are the newish plots. The other method was correlation. A template profile is correlated with the current profile, and a difference greater than a set threshold is taken as a damaged edge. The plot shows the correlation function. With good edges there's a noticeable peak, and with damaged edges the peak drops. As I have mentioned before, the change in color is for clarity. The orientation of the camera is also important when carrying out edge tracking. Because of pixel timing errors, this image shows how bad an edge can become if the pixel clock is put out by a single pixel. If the strip edge was aligned 90 degrees to the rows, this would reduce accuracy due to the pixel timing errors. This is the lab setup that I used to develop the system. The computer is an IBM PC XT compatible, running at 12 MHz. The frame store has a maximum grabbing rate of 5 frames per second. It has two frame buffers, each of 132 kilobytes, and its resolution is 512 columns by 256 rows. The overhead projector is used as the lighting because it has an integral Fresnel lens, which helps to spread the light more evenly over the scene. I would like to thank Sheffield Hallam University Television Production Unit for their help in producing this video.